Welcome back to another lesson on trigonometry. You'll see here that I've summarized the results from our previous lesson. Remember how these values were obtained from geometry, specifically the equilateral triangle, the square, and the pentagon. Then we used a couple trig identities to obtain the other values. We also saw how trig identities can be used to find the value of angles at every 3-degree increments. Here I've summarized just a few of our angles. Notice theta in degrees is in the left-hand column, and the sine of that angle is in the right-hand column. Now what happens if I were to graph these? Theta is my independent variable. It is my input. Sine theta is my dependent variable, the output. So to bring it back to terms we used in previous lessons, this would be the x and y. So it's simply plotting the coordinate pairs on the Cartesian plane. So this is more or less how the plot is going to look. Now notice a straight line might be okay for the beginning of the curve, but if I were to continue, that wouldn't work out so well. It's curving down. This is a nonlinear graph. Okay, it's got that curve to it. What if I wanted to know the value of theta equals 58 degrees. So sine of 58 degrees, well, we don't know that. Is it on our table? No. And even in the other one of 3-degree increments, we jump from 54, 57 to 60. It's not on our table of exact values, so how are we going to find that? This is where we introduce the concept of linear interpolation. Linear interpolation basically falls back to the concept of point-slope form, where we use a point and the slope. Or in this case, we're going to use 2 points to find our answer. So let's start with that. Point-slope form, y equals m times x minus x1 plus y1, where m is equal to y2 minus y1 over x2 minus x1. So what do we have to do? Well, we pick 2 points. Now, it could be any 2 points, but we'll see here soon that there are better ways of choosing those than others. Let's pick 54 and 60 because 58 lies somewhere between these 2 numbers. I'm going to pick off the values. If this is x1, y1, x2, y2, I'll plug it into here. So m is equal to y2 minus y1, x2 minus x1. Now let me plug that into my calculator. So I get approximately 0.009501 as my slope. Now let me plug it into there. X is going to be my 58. That's my input variable. X1, well, that's going to correspond to 54. And Y1 is this guy. So I get approximately 0.847022. So the exact value of sine 58 degrees is 0.848048. So our answer here is a pretty close approximation to the exact value. Now what if there's a way to make it closer? Notice we picked 54 and 60 from our table here. What if instead I chose 57 and 60? 57 we can obtain from our other table. So slope is going to be y2 minus y1. From our more complete table, I've obtained the value of sine 57 degrees. So I have y2 minus y1 over x2 minus x1. The slope is approximately equal to 0.009118. Now, I'll plug that into my point slope form. And I get 0.847789. Notice how this answer is closer to the exact value than our previous answer. So in short, by making a narrower range, by closing in the gap, we get a more accurate answer in interpolation. What does this look like on the graph? Well, if these are 15-degree increments, 15, 30, 45, 60, 75. So 60 degrees is here, and 54 degrees is here. So notice this line is curved, but we've run a straight line approximation through that. So this is our linear approximation between these 2 points. There's a good point to make. The difference between interpolation and extrapolation. Interpolation is between these 2 points. Notice, just from looking at the graph, that's a reasonably close approximation. Extrapolation is when we go beyond the bounds to either the right or the left. Now you see the pitfall there? And once we get out here, it's nowhere near the true value of the graph. Always beware of extrapolating. But it comes from the same linear fit. Okay, so we've mentioned that picking 2 points closer together gives us a more accurate result when we're approximating a value in between those 2 points by interpolation. For example, if I were to pick this point and this point and draw a line between them, well, that wouldn't be a very accurate representation of what's going on in the middle. If I were to pick points closer to the middle, say this point and this point, well, that gives me a little closer approximation. And then if I go to these 2 points, which are closer still, well, now our answer is getting even closer. So we can approach the more exact value. Let's take a timeout to talk about the bisection method. So far, we've spent a lot of time finding the exact trig values of various angles, deriving those from geometry. And then we've been using the trig identities to further expand our table. Of course, that has limitations in that there are gaps of every 3 degrees. So in our previous example, where we are looking for 58 degrees, that is not divisible by 3. It is bound by 57 and 60, according to our table that we've constructed. Linear interpolation was presented, and that is a way to approximate this value. Another way is to bisect that angle. Now, bisecting basically means cutting in half. So halfway between 57 and 60, which are the known values, we can use trig identities to find the sine of, well, halfway between 57 and 60. 57 plus 60 divided by 2 is 58.5. So we can use trig identities to find the sine of 58.5. Notice we're now slightly closer to our target. Now, this falls within a new region. So halfway between 57 and 58.5, we'll add these up and divide by 2. We get 57.75. You can verify that on your calculator. Now, all right, we're closer still to our target of 58. And I have a new region that I can cut in half. So halfway between this number and this number, add them up, divide by 2, and we get 58.125. So notice we're getting closer and closer each step. In the first case, we were 1 degree away. Then we cut that in half, and again in half, and again in half. So each time we're getting closer and closer. Notice also, in this case, we're bouncing back and forth between upper bound, lower bound, upper bound, lower bound. And it's jumping back and forth as it's converging on 58. This is certainly a possibility. But if you try it, you'll find that it becomes a lot of work very quickly. For that reason, I discourage use of this method in favor of other methods, one of which we will discuss next.